Hi, I'm Andrew Freeman from the University of North Carolina at Chapel Hill, and I will be presenting our work, Motion Segmentation and Tracking for Integrating Event Cameras. To begin, I'm going to give some of the background about event cameras and the current camera landscape before discussing our previous work. So from the 1870s pretty much until now, we've been operating under the framed camera paradigm. So the earliest cameras, film cameras, captured the world with discrete image frames. Then as we moved into the digital era with digital single lens reflex cameras and point and shoot cameras, that continued operating under that same assumption. And with the smartphone revolution more recently, with everybody having a camera in their pocket, still we are capturing the world with discrete image frames, which is fine. It's been very useful in a lot of ways. It's given us lots of possibilities, but the problem is, and what our thesis essentially is here with our work, is that this is a problem in some respects because it is not how the human eye captures the world. It's not how we as humans actually process visual information. So what we propose is that the future of imaging is going to be frameless. And we've already seen the camera landscape start to shift towards the frameless paradigm with the development of DVS style cameras. So DVS stands for Dynamic Vision Sensor, and this is the prominent neuromorphic camera design today. Neuromorphic meaning it attempts to emulate the way that the human eye operates in this case. So DVS cameras have been around for a few years. There are commercial products that you can buy. You can go out and purchase a DVS style camera if you want to. And these cameras, instead of capturing framed images, the pixels on the cameras will instead output asynchronous polarity events. When the pixel value, the intensity on that pixel, changes across a predetermined threshold. So if the pixel gets a certain amount brighter, it'll output a positive polarity event, and if it gets a certain amount darker, it'll output a negative polarity event. And those events also have a timestamp, and they use that to basically represent a continuous stream of information. And these cameras enable high speed and high dynamic range capture, but not very high fidelity yet. There's kind of a kludgy way that researchers have taken so far of correlating these DVS style events with traditional framed images by having traditional active pixels on the same kind of macro pixel on these sensors to try to get some of that high fidelity back, capture the world more like how we see it as humans. But so far the results have not been what you would maybe expect coming from the framed image paradigm. So these cameras, because they're high speed and high dynamic range, they're really useful and used primarily right now for robotic sensing tasks and computer vision on robots. Now we argue that in order to have true high fidelity, high visual fidelity, the values coming from asynchronous pixels actually need to include information about the intensity across that pixel directly. So they need to directly measure intensity. And so we have previously proposed this asynchronous integration pixel, otherwise known as ASINT, where the pixels actually integrate light continuously, and the events that they fire out are not polarity change events, but rather they are firing events when the light that the pixel is integrated exceeds a threshold 2 to the d. It will output an event with d and delta t. And so then we can get the incident intensity directly from that value. So it's just 2 to the d over delta t. And so this allows us to theoretically get high speed, high dynamic range, and high fidelity capture without the need for the kind of kludgy approach with traditional active pixels alongside DVS pixels. So we can just directly measure the world with intensity values in an asynchronous manner. Now, in our previous work, we discussed how there is not a physical working prototype of an ASINT style camera yet. So in the meantime, anticipating the development of such a camera, we have chosen to emulate the camera in software. So we've developed an emulator that can read in still image frames or video into an emulated sensor, perform pixel-wise integration, emulate pixel saturation and changing the D values, the sensitivity of pixels, and then writing out those events to a file stream. And then more recently, we published this work about lossy compression of the data coming from this ASINT emulated sensor. So we divided the emulated pixel array into uniform blocks and had a couple different approaches for compressing the data within those blocks, depending on the stability of those pixel values over time and how much they differed from each other. But question we faced was, because it was very difficult to extend, it was difficult to add on top of this and continue to develop it, is why should we have this completely ground up approach of trying to reinvent the wheel? Why throw away decades of video codec techniques and research and refinements when essentially, fundamentally, this is still video data. It's just a different type of video data. So our new approach is trying to take some of the techniques from classical framed video compression and apply them in an asynchronous context. And that brings us to our new camera design, which we introduced in this paper. Here's the full diagram of our transcoder and encoder schemes, and we'll go through each of these pieces one by one so we can trace how it all fits together. So to begin, because we don't have a physical async camera yet, our transcoder here is just our emulator that I showed before. So taking frame video input and converting that to an async style event representation. So we then read our events into our encoder, but we only read in enough events to saturate an interval delta t ref. So this unit of time is a user-defined amount of time, and this basically constitutes our frame in an asynchronous context. So it's not a discrete image sample, but we're basically calling all of the events across a given amount of time across the whole sensor array to be a frame. So we're building that analogy to traditional framed compression schemes. And then from those events that we read in, we perform a delta t bit shift. So we're going to bit shift every single event's delta t value, which is the time value since that pixel previously fired an event. Shift those delta t values to the right by a user-specified factor lambda. So this is a pretty simple, straightforward way of compressing the temporal granularity of all of the events. We then need to decide if the current frame is an iframe or a p-frame. And to start, we'll look at the case that is an iframe. So this means the frame will be intra-coded, just looking at the data within that current frame. If this isn't the first iframe in a sequence, then we need to here perform delta t synchronization because the previous frames may have had different numbers of events that basically ended with the last event at a different time. So we have to account for that by having this filler delta t so that the next iframe has all events starting at the exact same reference point. So we fill that in, then we perform intra coding by, in a similar manner to our previous work on lossy compression, where we look at all of the pixels within a given spatial block, and we're going to intracode their prediction residuals for this frame period, this amount of time. Now, if our frame is a p-frame, then we get to perform residual coding from the previous frame. So we will take in a reference frame, and then we can actually do motion estimation. We described a distance metric in our paper. I'm not going to get into those details here, but essentially allows us to look at each block of pixels spatially and figure out how far away that block's events are for the current frame compared to different block locations in the last frame. So therefore, we can try to minimize the differences between the events in the current frame and the last frame and use residual coding to try to make as much of those events be close to zero as possible. And of course, all of this will help us when we get to our final step, which is our source model entropy coder, which takes all this data and compresses it down quite nicely for our final output. Now, the second half of our paper focuses on applications of an async style sensor and an async style representation of existing frame data. So to begin, we discussed a direct motion segmentation technique, which is a bespoke from the ground up built application for such asynchronous data. So the question is, how do you perform motion segmentation in asynchronous context when you can't do regular frame differencing? As an example, we're going to take a look at this input video. It has a bunch of moving objects in a pretty dynamic scene. And here we demonstrate that we can simply look at the event firing rate on each pixel, and we can threshold based on that. So here, every white pixel that you're seeing is if that given pixel fired more than 2 events over the given reference interval, that's delta t ref from the slides previously, and every pixel that's black did not exceed that threshold. Now with simple morphological closing, we can fill in those gaps and obtain a pretty clean segmentation mask of all these moving objects. And we're doing this while only looking at a single delta t ref interval of time. So that's essentially equivalent to only looking at one frame of information in a framed video context, but still being able to obtain a segmentation mask, a motion mask. Here we can see the result of applying that motion segmentation mask to the original framed video. And then here we can look at the four side by side. Now we next wanted to try applying a classical computer vision application in an asynchronous context to this emulated ascent video. So here we have object tracking in temporal foviation. Now the goal here is to track a single moving object, and this is a diagram of our pipeline if we were to have an actual async camera, but for the purposes of this paper, again, this async camera is being replaced with the camera emulator. So, but if we suppose our async camera is capturing information, then we can actually look at discrete image samples from that camera's memory and build a regular framed image from that, because we're just looking at each pixel's value in memory at a discrete point in time. We can plug that image into a traditional classical object tracking algorithm, obtain the object's new track position using the information about its previous location from previous images, and then we can adjust the camera's D values according to how far each pixel in the image is from this object. So then we essentially want to, now to underscore that last point, this video shows the effect of this kind of dynamic region of interest based D value adjustment. So we're going to set the pixels that are far from the object being tracked to have a very high D value, meaning they are not very sensitive, so they can accumulate light across several input frames for a long amount of time. And the pixels that are close to the object being tracked will have a lower D value. They will be more sensitive, so they can respond quickly as the object moves across the scene. And this kind of blurring effect that you see here, we're calling temporal foviation. So it's similar to spatial foviation, where the pixels just are blurrier and in lower resolution as you get further from a given region of interest, except in this case, the blurring is actually occurring across the temporal domain, not the spatial domain. Now, our goal here is to evaluate the compression potential of an asynchronous representation for this given application. So we set up this experiment using the NFS high-speed tracking dataset, which consists of 240 frame per second videos, wherein both the camera and the subject are moving in most of them. We had the following transcode parameters. Details on this are in the paper, of course. And we compared just a single object tracking algorithm, multiple instance learning, on both the ground truth image sequences and discrete samples of the asynchronous representation. We evaluated the area under the curve score with the ground truth bounding boxes for the first 200 frames. And then we evaluated the source modeled event compression, our new codec design introduced in this paper, against H.264 compression of the discrete image samples. This graph shows the results of running the tracking algorithm on the ground truth image sequences versus running it on discrete image samples of our temporal foveated asynchronous representation. So a score of higher than 0 implies that running it on ground truth performed better. A score of less than 0 means that running it on our asynchronous representation actually performed better. So on average, our score was 0.92 across all these sequences, which really tells us what I mentioned before, that we don't actually need the visual information outside of the object being tracked in order to have an accurate track, which intuitively makes sense. And we compared as well the compression performance against H.264, and the majority of our compressed videos of our asynchronous representation actually performed within the 1 to 2 times range of the compressed size of H.264, meaning that we're very close to having similar levels of lossless performance as H.264, but we're doing all of that while encoding a lot of information that we can't actually get with H.264, and that is the pixel histories encoding in the D values, up to 12,000 effective frames per second in this case because of the temporal granularity that we have, and then dynamic region of interest mappings, which can be recovered from our asynchronous representation. Now, there's obviously a lot of work left to be done. We intend to incorporate more robust prediction with B-frames. So by prediction, look at both the frame that came previously and the one coming after to inform the motion estimation. We want to improve our distance metric and the search speed for finding a matching block in a different frame. We want to incorporate more performance improvements to approach real-time encoding performance. We've made a lot of progress in this since we submitted this paper actually, and have since shifted most of the processing to the GPU. And we want to work more on bespoke asynchronous applications. We've also done a lot of work on this since submitting the paper. Currently working on animal breathing rate analysis by casting traditional frame video into our asynchronous representation. And then finally, we want to work towards a unified system for representing DVS data as well in an ASIN style format. So far we've only created a transcoder for taking traditional frame video and pushing it into an ASIN style format. We want to do the same kind of thing for DVS data, because we really think that an ASIN style event is going to be the best way to represent visual information in an asynchronous context.